Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.
A change in an observed wave frequency when a source moves with a speed. For instance, if a siren, a vehicle that is producing a sound or is moving past you, there's a way the frequency changes, the pitch changes. Have you ever observed that? Whether when it is moving past you or approaching you? Not necessarily louder. Okay, you mean the pitch increases. When it is moving away from you, receding from you, the pitch decreases. You would have heard something like this. You know, that's kind of sound. Maybe an ambulance passing. It's not just about the loudness, but the pitch too. Well, that's a general principle we call Doppler effect. When an object is approaching you with a speed and producing a particular frequency, the frequency increases as it is approaching you. You are a stationary observer listening to the frequency. The object could be a car playing a sound or producing a sound, a siren for instance, approaching. Because of the motion towards you, the frequency of the sound wave that is coming out from that car increases, the pitch increases. It increases in pitch from low to higher pitch. You understand what I'm saying? But if the car is moving away from you, the pitch decreases. Well, that's what we call Doppler effect. It's not only in this. By the time we get into space physics, we'll talk more about that because we also use that in describing the behavior of the universe. You remember when we were looking at that at O levels? All right. There's more to talk about that at this stage of your program. So Doppler effect is the change in the frequency of sound produced by a source when an observer is listening to that sound from the source coming towards the observer or moving away from the observer. So generally it's the observed wave frequency when a source moves with a speed, Vs. Now that observed frequency, F0, is equal to Fs times V divided by, open the bracket, V plus or minus Vs. I will define each of these. I said the observed frequency F0 is equal to Fs times V all over, open the bracket, V plus or minus Vs. Now, the Fs, of course, is the frequency of the source. For instance, a car just zoomed past you with a frequency of, say, 500, producing a sound of frequency of 500 meters per second. You're noting down the formula. I need you to write down each of these. All of these. First of all, the formula, observed frequency F0 is equal to Fs times V all over, open the bracket, V plus or minus Vs. So I was trying to tell you that if the car moved past you and the car is producing a sound, maybe the frequency of the siren is, say, 500 meters per second, 500 hertz is the frequency of the siren. And you know the frequency of sound in air. What's the frequency of sound in air? Well, I said speed of sound in air is what I meant. Sorry. That's for light. 3.0 times 10 to the power 8 meters per second is light. Exactly, about 330 meters per second. In air, it's about 330 meters per second. That's the speed of sound in air. You know, sound moves faster in solid than in liquid, and faster in liquid than in gas, because sound is a longitudinal wave, and the closer the particles, the faster the vibration is transferred. Alright, the speed of sound in air is about 330 meters per second. That's what you should always use in this formula. If it is moving through air, of course. 330 meters per second. Now the speed of the source is Vs. Assuming the car is moving at 20 meters per second or 30 meters per second. If the car is moving at the speed of 30 meters per second, or let's even say 50 meters per second, we can use this to calculate the observed frequency, what you will hear as the observer. Can we apply it with this simple information we have here?
So should I also write down what the difference is?
Well, you should write. You want to write down what? No, we have done all this. We did intensity and all of that. It's in the previous note, the previous work. So you don't need all of this. Just a recap. But you find it in the other Java, but you can still take note of it. It's just a recap of part of the things we've done in wave. But I need you to note when we use plus and when we use minus. When do we use? Because the formula is observed frequency is equal to Fs times V over, open the bracket, V plus or minus V, Vs, close the bracket. When do we use a plus? When it's separating. When do we use a minus? Please, in separation we use a plus. When the object is approaching you, you use a minus. Please, you need to know, because I'm not sure this formula is provided among your formula table. So you need to know, think about it. Let me tell you how you can reason it out. Are you ready to listen to me?
Yes.
It's very easy to figure out when to use a plus and when to use a minus. You know, if the object is approaching you, the observed frequency will be what? Higher, isn't it? The observed frequency will be higher. So what do you think should be here? Let's listen, all of us. What do you think we should use here so that you can make this F naught bigger? Should it be a plus, a minus? It should be a minus. It should be lower value. It should be a lower value. You know, if you have something divided by a smaller number, it will produce a higher quotient. So when it is approaching you, you use a minus, so that the observed frequency will be higher. You get what I'm saying? Now when the object is moving away from you, you use a plus.
So Vs is speed of source.
Vs is the speed of the source, like the speed of the moving car. Fs is the frequency of the source, like the sound produced by the source. And of course, V is the speed of sound. We take a number of examples to explain this proper. Can we use this simple illustration I have here? A car is moving at a speed of 50 meters per second and is playing or producing a sound from a siren at 500 hertz. Of course, we know the speed of sound in air is 330 meters per second. What will be the frequency of the observed frequency of the sound that an observer can hear? Can we calculate? Let's use those values. So F naught will be, can we substitute? That's the example. Remember, this is all about Doppler effect. So F naught in this case will be, let's do the substitution.
I wait first.
Pardon? I'm using this. The question is this example I gave initially. A car is moving at a speed of 50 meters per second, approaching you, an observer. The frequency of a sound produced by the car, for instance, the siren, is 500 hertz. We know the speed of sound in air is 330 meters per second. So what will be the frequency that you, the observer, will hear? The car is approaching you. Okay, so let's substitute those values. Fs is 500. That's 500 hertz. 500 hertz times 330 divided by, open a bracket, V, the speed of sound in air, 330. This time around, it's approaching. Are we going to use minus or plus?
We use
Minus. Minus 50.
589.28.
So 589.28. 589 hertz. Or since most of them are in two significant figures, it could just be 590 hertz. It's as simple as this, but we need to try a few questions to illustrate this. Swung at a constant speed in a horizontal circle like this. That's an observer, a distant observer. The horizontal circular path of the source has a radius of 2.4 meters. Radius of 2.4 meters. And the source moves with a speed of 12.0 meters per second. That's the source of the sound, moves with this speed. And emits sound of frequency 951 hertz. The speed of the sound in air is 330 meters per second. An observer standing a very long distance from the source hears the sound. Calculate the minimum frequency to three single figures of the sound heard by the observer. It should be easy. Let's go. What do we have the important data. We have the source speed, and we have the source frequency, and we have the speed of sound. And it says the minimum frequency that the observer will hear. Listen up. Minimum frequency. Please let's get this right. For minimum frequency, are we going to use the plus or the minus for the formula?
That is plus.
Remember the F naught is Fs times V all over V plus or minus Vs. So for the minimum frequency, are we going to use the plus or the minus? Plus, that will give us the smallest, isn't it? Alright, so let's just substitute. Very good. Let's go. Pardon?
951 hertz.
This 951 hertz. 951. So F naught will be equal to Fs, the frequency of the source, 951, you said, times V.
The answer is 917.6.
Okay, speed of sound is 330. This formula, you need to use it properly. Okay, let's go. You've got the answer. Okay, 330 over
951 times 330 divided by 330 plus 12.
plus 12. And you got what?
917.63.
917.63. It says we should leave the answer to how many seven figures?
63.
Yes.
That's 917.63
To 3 significant figures, okay. 3 significant figures.
917. Okay, 920. 920.
I thought you said 917 points what?
Significant figures.
917 point what again?
0.632.
0.632, okay. 0.632 or 632. So what should it be to 3 significant figures? 980. You are stopping at the third significant figure. This is first, second, third, and this is already more than 5, so it should be 918. So this is 918 hertz. All right. The next question. The circular path of the source has a radius of 2.4 meters. Are you ready? Yes. The circular path of the source has a radius of 2.4 meters. Let's clear this very quickly. Determine the shortest time interval between the observer hearing a sound of minimum frequency and the observer hearing a sound of maximum frequency. The shortest time interval between this observer hearing a sound of minimum frequency and the observer hearing a sound of maximum frequency.
So, are we going to find the frequencies?
The time interval between hearing highest frequency and hearing lowest frequency. The time intervals between hearing highest frequency and hearing low frequency. Remember, he's moving around this circle. At this point, he hears the highest frequency when he's approaching. Is it not? Let me call it point A. At this point, when the source is farther, it hears the lowest frequency. Is it not? Because it approaches, when it's approaching, the frequency increases. Is it not? When it is receding, going away, the frequency decreases.
So, calculating the time interval.
Yes, the time interval.
So basically, we're just calculating the time interval between when it's at A and when it's at B.
Simple. We are just getting the time interval when it is at A and when it's at B.
So, do we now calculate, use the radius, not calculate the distance?
Beautiful. The radius is given as 2.4 meters.
So, now use the speed.
Okay, distance time.
Distance time formula. The radius is 2.4 meters.
Yes.
It is when it is coming that he hears the highest frequency. Am I right? For it to hear the highest frequency again, it should be when it's coming again.
Okay, so calculating the circumference then.
The circumference of the circle. The circumference is pi d.
And it's not 2 pi r.
Or 2 pi r, or simply pi d. Circumference is 2 pi r or pi d. Okay, circumference of the circle. The speed of the source is 12 meters per second.
Yes.
All we need to find is the circumference of the circle, because as it is coming closer, you hear the highest. For him to hear the highest again, he has to complete the circumference. And you know, from your distance time graph for junior school, from distance time graph for junior school, speed is equal to distance over time. And we're looking for time interval. So time will be equal to what? Distance over speed. Simply t is equal to distance, you can call it s over
Circumference is 15.
speed. And the distance is the circumference, which is 2 pi r.
15.1.
So 2 times pi times, what's the r?
R is 2.4. Circumference is 15.
2.4. Okay, over the speed. What's the speed? What's the speed of this guy? The speed 12. Okay.
Outside is 1.2.
So over 12. So that gives us 1.1. What did you get?
1.26.
1.26. So the time interval from when he heard the highest frequency at A to when he hears the highest frequency again at A will be after it has completed a full circumference. A full circumference. So the time interval from hearing the highest frequency at A and hearing it again, that same highest frequency at position A, is what we got as 1.26. But the question is, determine the shortest time interval between the observer hearing sound of minimum frequency and hearing maximum frequency. So for minimum frequency and maximum frequency was heard at A when it was coming closer to the observer. That's for maximum frequency. Minimum frequency is at B when it was moving away from the observer at the highest position. So we have to divide that whole time interval into two. That's the time interval from hearing the highest frequency at A and hearing it again at A, which is a full circumference. We need to divide it into two so that we can get the time interval between hearing the highest frequency at A and hearing the lowest frequency at B. In other words, we can also use this half of a circle, half of this circle as our distance. There are two ways to do this. It's either when we're doing distance over time, we simply use half of a circle, which would have been just pi r, not 2 pi r, for our distance divided by the speed to get that time interval. We could have done it that way because it is about highest frequency and lowest frequency, the time interval. So it's just half of a cycle or half of a circle. Alternatively, the way we have done it, which is finding the time interval between hearing the highest frequency at A and hearing it again at A, that same highest frequency, which of course is the full cycle. So now that we have gotten the time interval for the full cycle between hearing the highest frequency at A and hearing it again, to now get the time interval between hearing the highest frequency at A and hearing the lowest frequency at B, we divide the answer we got by 2. So this answer should be divided by 2. So what we are looking for should be divided by 2. This, I can call this one the total time interval, but what we are looking for, T, is equal to 1.26 divided by 2. 1.26 divided by 2. So we divide by 2 and we're going to get divided by 2. That's going to give us I think that should be 0.63. This divided by 2 will give us 0.63, which is the answer. So the answer is actually 0.63 seconds. 0.63 seconds. Okay. Now this is the full workings. You can zoom it in a bit to reveal it better. The question, starting from here. This is what we are given. We found the first part, 918 hertz, and the second part, 0.63 seconds. That's that. Okay? Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to two main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.